This video is part 2 of the Introduction to the Retractable Roof Production System, or RRPS. We saw in the first video how tomato young plants from the same tray developed in the open field, a stationary roof house, and a retractable roof house. While the genetics of these plants was identical, the differences in the growing environments caused the plants to develop different heights, leaf size, and quantity and size of fruit. You will now see in greater detail the impact of the direct sunlight and a roof covering on soil and plant temperatures, which will help explain why plants in the different production systems always look different. It is 12:50 on April the 13th, 2011, and we are in the retractable roof house in Culiacan, Mexico. We're going to do a check of the leaf and soil temperature, both in full sun and underneath the retractable roof. So it is 12:50 in the afternoon, and the relative humidity is 40%, and the soil temperature in the direct sun is 53 degrees Celsius. Using an infrared temperature sensor, we are getting similar values up to 55 degrees Celsius. The air temperature currently is 36.6. Looking at the plants, you can see the leaves are not flagging at all. They're very firm. And the underside of the leaves are quite clean. Now, looking at the impact of the roof on the leaf temperature, where the sun is coming through the opening in the roof, the leaf temperature is measuring 34, 33 degrees Celsius. When we move up higher under the shade from the retractable roof, we're now measuring 25. 25. So we are going from 25 under the retractable roof to 32 Celsius, which is giving us a 7 degree Celsius difference in leaf temperature. This infrared radiation is positive in the morning because we want the sun to warm up the leaves. However, during the heat of the day, we want to reduce the radiation and transpiration so that the plants stay active throughout the day. To further demonstrate the impact of direct sunlight on soil temperatures, this picture was taken at 1:11 p.m. in Mexico. The air temperature is 32 C, but the soil temperature is 69 C, which is a 36 degree higher soil temperature than air temperature. Looking at fruit temperatures on another day, the air temperature was 28.6 C and the fruit temperature in direct sunlight was 42 C. This high fruit temperature helps explain why yields are so low in the open field, as temperatures and light intensity increases in the summer. Since air temperatures is such a poor predictor of plant and soil temperatures when they are exposed to direct sunlight, the RRPS uses infrared temperature sensors since they give a more accurate reading to what the plant and soil temperatures really are. The infrared sensors can also be a good predictor of overall plant health and function. This picture is of a tomato plant that is not healthy. You can see that the leaf temperature is 47 C when the air temperature is only 34 C. This tells us that the plant is no longer transpiring sufficiently to cool itself. In another example of how infrared temperature sensors can help us make better decisions, this picture of lettuce was taken at 12:08 p.m. on March the 1st, 2010, near Orlando, Florida. You can see that the air temperature is 29 C and the leaf temperature in the shade is 17 C. When we then measured the leaf temperature in the sun, the leaf temperature increased from 17 C to 27 C, but the air temperature was still 29 C. What is significant is that the leaf temperature increased by 10 degrees C, but the air temperature did not even change 1 degree. This tells us that the RRPS allows growers to grow at lower air temperatures if the sunlight is shining directly on the plant, thereby reducing the need to burn fossil fuels to increase air temperatures. When the roof is retracted, the plants receive full infrared radiation, warming the leaves and fruit, helping to dry condensation, which explains why foliar diseases are virtually eliminated in the RRPS. Retracting the roof also exposes the plant surfaces to ultraviolet radiation, which sterilizes exposed surfaces and helps plant develop their natural colors, particularly red and yellow. Another way that the RRPS can be used to reduce the use of fossil fuel for heating is to retract the roof on a sunny day before a cold night. The direct sunlight will heat up the soil in the daytime, helping to create a heat sink in the earth. The roof is then closed when light levels drop to trap the heat in the greenhouse. The ground will then release the heat throughout the night, helping to protect against cold damage. This strategy protected tomatoes in Sinaloa, Mexico from temperatures which dropped to -4 C for 6 hours. This chart is from the computer that was controlling the retractable roof. You can see that the black line is the outdoor black plate temperature, which dropped to -4 C for 6 hours. However, the indoor soil temperature stayed at 17 C throughout the night, consequently releasing enough heat to help keep the indoor air temperature above 0 C, thus preventing significant loss of crops. One more strategy for how the RRPS can be used to reduce or eliminate fossil fuel for heating is that the excellent cooling properties of the RRPS allows production to move to warmer climates where conventional greenhouses are not well suited. Since air temperature is such a poor predictor of plant and soil temperatures when exposed to direct sunlight, the RRPS uses a black plate sensor to provide a more accurate temperature reading to determine when to close and retract the roofs. This sensor is installed on the weather station outside. The black plate temperature changes as changes occur in light levels, air temperature, and wind. Looking again at the temperature chart from February 3rd and 4th, 2011 from Culiacan, Mexico, you can see that on the second day, the black plate temperature outside increased rapidly from a low of -4°C, reaching a high of 37°C, whereas the air temperature only reached a high of 23°C. When the black plate temperature drops below 15°C, the roof closes to trap heat. When the black plate temperature exceeds 17°C, the roof retracts, exposing plants to direct sunlight. And when the black plate temperature exceeds 28°C, the roof closes 85% to 90% to prevent exposure to excessive heat. Extreme weather automatic overrides includes a rain sensor to close the roof when it is raining, a wind sensor to close the walls and roof to protect plants, and an optional barometric pressure sensor to close the roof in advance of extreme rainstorms or hail. Growers using the RRPS can avoid the problem of salt accumulation in the soil, which typically occurs when producing using a conventional greenhouse production system. When salt levels in the soil become excessive, the roof can be left retracted when the house is empty to allow the rain to enter the house and help leach the salts. This grower in California has been using this strategy of retracting the roof when the house is empty and has been producing peppers and cucumbers in the same soil for 13 years, thus eliminating the need to either change the soil or switch to a hydroponic system. In summary, the Cravo Retractable Roof Production System is a tool that scientifically helps growers automatically create the best possible growing conditions by reacting to changing weather conditions in minutes to profitably produce food crops, flowers, trees, and shrubs. The RRPS helps growers create sustainable farms of the future by increasing revenues through higher yields and quality while extending the harvest season. The higher yields allows growers to reduce their fixed production costs by reducing the area under cultivation, while simultaneously reducing water usage, chemical usage, energy costs, and labor costs. Full implementation of the RRPS frequently allows growers to realize a 2 to 5 year return on investment.